Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back, and we're going to continue to discuss this jump to contact phenomenon and try to better understand what the implications of that snap to contact of the tip to the substrate, what implications that might have for understanding experimental data. So this is more of a slide more to remind you of what we discussed in the last lecture. It's important to understand this, the processes involved in this, in constructing this slide, and in particular, it's important for you to remember the sign conventions that we use when we discuss the deflection of the cantilever Q. So that little cartoon up there in the upper left is an important diagram that we'll use not only through this lecture, but through the next 2 or 3 lectures. And it also is the same sign convention that I believe Veda uses when Veda simulates these experiments that we're talking about in a schematic way right here. Before we proceed, I'd like to talk a little bit about the total interaction potential that the tip experiences when you move a tip close to a substrate. And this total interaction potential has 2 components. One component is the harmonic well that the tip oscillates in. So if there were no tip surface interaction and you position the tip at a certain distance above the substrate, let's say that distance is located by this point A, right? Then if you gently hit the tip would oscillate back and forth about its equilibrium position. And the potential well that describes that oscillation is that quadratic well that's labeled by the word cantilever potential. Now, in addition to that, there's the interaction potential. Now, this is not the force, this is the interaction potential energy that the tip experiences as it interacts with the substrate. And that interaction potential energy is indicated by the solid black line that goes either negative or positive about the U equals 0 axis. And so the net interaction potential energy that the tip feels is going to be the sum of those 2 curves. Now, if the tip is far away from the substrate, let's say at point A, right, the total interaction potential energy is going to be dominated by the cantilever potential in general, right? And we'll have a quadratic-looking curve as indicated in the upper right. As you move the tip closer to the substrate, then the actual distortion of the interaction potential energy due to the tip-substrate interaction comes in. The quadratic potential well starts to get distorted, as I've indicated by this circle line, which schematically indicates the type of effects that you're going to see. So this isn't terribly relevant. The shape of this potential well, this total potential well, is not terribly relevant for the discussions here. It'll be discussed more in part 2 of the course, but I wanted to at least point this effect out and then use it. I want to use this concept of the total potential energy to discuss the stability of the tip with respect to the substrate. So if you go back and you think about your introductory course in physics, right, you could model many different processes in terms of the total interaction potential energy. And in particular, the second derivative of that total interaction potential energy gives you a criteria for deciding whether a particular condition is either in stable or unstable equilibrium. So I list the two extremes here. In one case, when the second derivative of u with respect to a displacement z, when that quantity is less than 0, we say we're in unstable equilibrium. When the second derivative of the total interaction potential energy with respect to z is a positive number, we say we're in stable equilibrium. And then clearly there's going to be a transition region where you go from the unstable to the stable regime, and that'll be given by the second derivative of the total interaction with respect to z when that's precisely equal to 0. So we're going to use that transition condition in the next slide to derive a simple expression that relates the jump to contact distance to the Hamacher constant of the interaction potential energy that's acting between the tip and the substrate. So this is worked out the arithmetic for that calculation is worked out in this slide. In particular, I won't go through the details because I think it's pretty straightforward. Again, it's one of those slides that you're going to have to sit down and look at on your own. But basically what I've done here is I've got two equations. One equation, which I call equation 1, equates the interaction potential energy of the tip substrate to the interaction, equates the force of the tip substrate interaction to the force exerted by the cantilever when it bends through a deflection Q. So that's indicated by equation 1 on this slide. The other equation, which I call equation 2, basically tries to calculate the point at which the total interaction potential energy, second derivative of the total interaction potential energy with respect to z, where that is equal to 0. That's the point that marks this transition from the stable to the unstable equilibrium, and in principle that's the point where the tip is going to jump to contact. So the result I get from equation 1 on the right-hand side of the slide, that's not terribly interesting. It just relates the distance d for jump to contact to the deflection of the cantilever q for jump to contact. That number is going to depend on the interaction potential energy through the parameter h, Hamacher constant. It's going to depend on the radius of the tip, capital R, and it's also going to be related to the spring constant K. So that's a nice result, but it's not terribly relevant. The result I like a little bit more is if you rely on equation 2 and you follow through the arithmetic, at the end of the day you'll find that you can get an expression for the deflection of the cantilever when the cantilever jumps to contact in terms of fundamental quantities like Hamacher constant and radius of the tip and the spring constant K of the cantilever. So in principle, what this equation is telling you is that if you can precisely measure the deflection of the cantilever just before jump to contact, you can measure that accurately, and if you know the tip radius and the spring constant of your cantilever, then you've got a way to, in principle, infer the Hamacher constant H that that you can use to model the tip-substrate interaction. And that's a very useful quantity to know. It's hard to measure H experimentally in a reliable way. This lecture plus the 2 or 3 lectures that are going to follow requires you to pay special attention to a lot of concepts that are closely related. Each concept is given a name, and that name is also given a symbol. And so what I tried to do here is I tried to systematically list down the various parameters that we're going to use. They're called Z, D, the deflection of the cantilever is Q. Cantilever force is always going to be given by the spring constant of the cantilever K times the deflection of the cantilever Q. So that's always going to follow. We're going to talk about sample deformations. The sample deformations are going to describe how the tip indents into the sample, and of course we discussed that a little bit in week 2. We laid the groundwork. Now we're going to actually start to measure what those deformations are. Right? There's a fundamental relation between D, Z, and Q, which I also list on this slide. It's a little bit confusing because Q is a sign quantity, which means you basically have to remember the sign convention for Q, or otherwise you'll get your axes twisted up. Experimentally, you're always controlling Z when you do an AFM approach curve. When you move the tip towards the substrate, you're controlling Z. And what you are doing is you're measuring Q by measuring the deflection of the cantilever by digitizing the output of the photosensitive diode. So you control Z, you measure Q, and then from that you can work backwards and infer D using the equation that I give, right? And of course the tip sample force, that's the thing that's fundamentally interesting. That has to be inferred from the measured cantilever force. And the cantilever force is always given by the spring constant K times the deflection of the cantilever Q. So maybe this slide is useful because it sort of tries to lay out all these things in a systematic way. I'd like to real quick go through a sequence of curves that we showed quickly in the last lecture. I'd like to do it a little bit more slowly here just to make sure everyone's on the same page. In particular, I'm trying to distinguish between the force versus gap distance, or distance, force versus distance, D, that's on the left, versus force versus displacement, which is F versus Z on the right. What you measure, of course, is the force versus displacement, and what you're trying to infer is the force versus distance curve. So initially, the way I like to think about it is I position my tip, which is attached to a cantilever with a spring constant K. The slope of that red line is equal to the spring constant K. We're now plotting the tip sample force versus the gap distance D on the left. So we position that cantilever at some point. The cantilever deflects through this distance Q, and we end up with a gap distance as indicated by the solid black dot on this curve. If we want to try to map out this entire force versus distance curve, what we continue to do is we continue to decrease Z, right? And finally we're going to reach a Z value in which the slope of in which the spring constant of the cantilever matches the slope of the F versus D curve. When we hit that condition, then we get a jump to contact. The tip abruptly snaps from point 2 to point 2 prime. In the experiment, that all occurs at the same value of Z, right? That all occurs at the same value of Z. Of course, the difference between Z and D is the deflection of the cantilever Q. So the cantilever suddenly deflects. The position of Z in principle is the same, and D changes as a result. Once the tip has jumped into contact with the substrate, then you can continue to load the tip into the substrate by decreasing Z. When you do that, you'll reach some final loading force indicated by 3 on this diagram. And then experimentally what you do is you withdraw the substrate from the tip, and you continue to withdraw the substrate from the tip until the slope, the spring constant of the cantilever K matches the slope of the F versus D curve at this point 4. At point 4, that means it's a point of unstable equilibrium, and the tip will then jump to point 4 prime, which means that the tip snaps away from the substrate. Now in this entire process, there's actually a region of the F versus D curve which is completely inaccessible. And the reason it's inaccessible is because the tip is jumping to the substrate, and it rapidly goes through a whole range of D values which you can't access. And then in the reverse part of the curve, there's also the same phenomenon, right? You can't access all the data points as the tip snaps away from the substrate. I also wanted to point out there's a very fine distinction between the pull-off force and the adhesive force of the tip with the substrate. Technically, the adhesive force of the tip versus the substrate is defined as the minimum in the F versus D curve. The pull-off force that you measure experimentally, that's related to the point on the F versus D curve where the slope of where the cantilever K matches the slope of F versus D. So in principle, there could be a slight difference between the pull-off force and the adhesive force that I tried to indicate by blowing up the bottom region of this curve here. So if you can understand this whole process clearly, then I think you've understood something about the nature of the F versus Z experiment that's a very routine experiment done in all atomic force microscopes. Again, here I just try to repeat the same curve shown in two different ways. The bottom curve is what you measure experimentally. That's plotted as a function of Z. The upper curve is an effort to try to summarize all this information by trying to keep track of Z and D in the same plot. It tends to be confusing, but if you remember the conversion between Z and D, maybe it's not so bad, right? Maybe you can understand in detail what's going on. So for the remainder of my time, what I like to do is I like to apply this understanding using a particular model and show you what the consequences of those models are. This is something that you can routinely do in the Veda simulation software, and we'll focus more on that part of this discussion in week 5 of the course. But basically, I like to just select the DMT model, and the assumptions of the DMT model that we covered in week 2 of the course are summarized in the first 2 equations of this slide. These equations are color-coded, red and blue, to indicate different regimes, right? So the important parameter in the DMT model, one important parameter in the DMT model is the equilibrium separation between atoms, and that parameter is referred to as A0. And so if your tip is farther away from the substrate by an amount, is away from the substrate by an amount greater than A0, then the tip sample interaction force follows the red equation at the top of this slide. When the tip presses up against the substrate and the separation between the tip and the substrate is A0, then you're looking at the blue equation, which is the second equation on this slide. There's a parameter E star, which is the effective elastic modulus of the tip and the sample. E star always has to be calculated using this formula that we keep showing over and over again. We'll use this repeatedly throughout the remainder of this course. It's useful to try to map Z and D, right? And there are 2 conditions that have to be met in order to do that, and those 2 conditions are given by the red and the blue equations at the top of the slide. And so the tip will be in equilibrium, right? The restoring force due to the bending of the cantilever will exactly counteract the interaction force between the tip and the cantilever. And it's interesting to find out where those equilibrium conditions are. And I do that in part A and part B on the right-hand bottom of this slide. I just set the DMT force equal to the force exerted by the cantilever, and I have to be careful to take into account the 2 conditions, D less than A0, D greater than A0. When I just set those 2 equal to one another, I get 2 equations, right, which I can then plot, right? At least as a theoretical exercise, because I can specify an H, I can specify an R, radius of a tip, I can specify an effective modulus E star. I can guess what A0 is. A0 is going to be on the order of 0.3 nanometers. That's typically the separation between 2 atoms. And so I have 2 equations that I can plot, Z versus D. And I just go through that exercise on the next slide, just to show you this is, again, output that Veda can achieve. But I wanted to show you how it gets that result, and I wanted to just discuss what it means in a real simple way. So if I just take these 2 equations for the 2 regimes, D less than A0, D greater than A0, I can make a plot of Z versus D, and when I do that, I get a plot that looks like the one shown in the left-hand region of this curve, right? And you'll notice that this plot has multiple values depending on what region of Z you're at, right? So there's region 1, where for any particular z, you've got a well-defined value of d, right? There's region 3, where any value of z also gives you a well-defined value for d. But then there's this intermediate region 2, where depending on what value of z I specify, there are 3 solutions for d, right? And those 3 solutions are indicated by the points A, B, and C. And right, those 3 solutions graphically are interpreted as the matching of the slope of the cantilever, K, with 3 points of intersection on this tip force versus distance curve. So A, B, and C on this force, on this tip, A, B, and C shown on the bottom region of this graph. In region 2, they match A, B, and C in the upper region of the graph. And of course, each region can be associated with a different physical phenomenon. Region 1 is the approach of the tip to the substrate. Region 2 defines the jump to contact and the pull off. And then region 3 is the actual indentation of the tip into the substrate. The way I like to look at this curve is I like to imagine a red ball rolling down this slope. Initially, as the ball rolls down the slope, Z and D are directly proportional to one another. The ball will roll down until it reaches the cusp of this curve, at which point it'll fall off. You'll jump to contact, basically. The tip jumps to contact. That's indicated by the leftmost dashed line. You can then load the tip against the substrate, and then as you retract, right, the tip will stay in the contact with the substrate until you reach a Z value where the rightmost dashed line just comes off the red curve and you jump away, right? So this is a very useful plot to understand if you want to really understand the relationships between Z and D. And of course, once you have the relationship between Z and D for a given model, you can always then go backwards, work backwards, and calculate what the deflection of the cantilever is as a function of Z, simply by using the definition between Q, D, and Z that I've got in the second graph of this slide. So again, you can see from that graph that as you start with large Z and you move to the left, if that red ball rolls to the left, right, Q is essentially equal to 0 because there's no tip surface interaction that far away. So Q is 0, no tip deflection. As you start to approach this jump to contact phenomenon, you can see that Q starts to bend negative. There's a jump to contact, so the tip jumps from one value of Z to or the tip at the jump to contact point, right? The Q value of the tip changes abruptly, and then you can load the tip against the substrate, and you'll follow the left-hand part of the red curve there. So these curves were generated using the parameters that I list on the upper part of the slide, and they give you an indication of how Veda is going to calculate displacements of cantilevers for different choices of parameters. And I'll end the lecture with another slide that illustrates the utility of these types of plots. This is a Z versus Q plot. In this case, I've done the plots for a variety of different elastic moduli, effective elastic moduli. I choose a very soft sample, 0.5 gigapascal. I choose a very hard sample, which is 1,000 gigapascal. And you can see the relationship between Z and Q for these different elastic moduli. The Hamacher constant, the radius of the tip, and the spring constant are kept fixed in these calculations. And the point to emphasize here is that the green curve is what you would expect if the substrate and the tip were infinitely hard. That's how the deflection of the cantilever is going to vary as you systematically decrease Z from some large value and load the tip against the substrate. Any of the curves, the blue and the red curves, show what you would expect if the tip substrate is softer, right? And so the difference between the, let's say, the green curve and the red curve at any value of z, that difference is simply the deformation of the substrate, the tip substrate junction that's going to occur for that particular value of z. Once again, the z equals 0 is an arbitrary number. That's something that it can be offset any way you want because you can't define z equals 0 in these experiments. So you need some other convention to set z equal to 0, and we'll talk a little bit more about that as the course evolves. But shouldn't get hung up over that issue. It's just a parameter that you can't identify precisely. I ran a little bit over time, but it's really worthwhile to understand these curves. These are curves that you can output from Veda, and they really help you understand the fundamentals of what's going on. The next lecture, we're gonna try to explain how to convert the approach curve data. That's the voltage from the photodiode versus z-displacement. We want to convert that into a force versus tip sample gap, which is a very fundamental quantity. So come back and that's the topic we'll discuss in week 4 or in lecture 4 of week 4. So thank you very much.